Even now, in this stillness, in this breath, something extraordinary is happening. Every particle that makes up the body is hurtling through the fabric of space-time at precisely 299,792 kilometers per second, the universal speed limit, with no exceptions, no pauses, no way to step outside the current. This is not metaphor. This is the strange and beautiful truth that Einstein uncovered more than a century ago, that motion through space and motion through time are bound together, trading places in a cosmic balance that cannot be broken, only understood. If these quiet explorations bring a kind of peace, subscribing is a gentle way to return. The mathematics are elegant, the implications profound, and the journey through them can be taken slowly, softly, without rush, for time, after all, moves at its own pace. And tonight, so can we. And here, the story begins. You are lying still now, perhaps on your back, perhaps on your side, and everything about this moment suggests rest. The ceiling above you does not move. The walls hold their familiar positions. If you have placed a glass of water on a bedside table, its surface remains flat and undisturbed, showing no sign of acceleration, no hint of motion. Your body presses gently into the mattress, and the mattress presses back. And between these two gentle pressures, there is what seems to be perfect stillness. You might reasonably conclude, based on all available evidence, that you are going nowhere at all. You might imagine yourself fixed in place, stationary, at rest in the deepest sense of that word. And yet, this feeling, this convincing sense of motionlessness, is one of the most profound illusions your nervous system will ever produce. The truth, which requires no faith to accept because it has been measured with exquisite precision across several centuries of careful observation, is that you are moving at this very moment at speeds that would seem, if stated plainly, almost absurd. You are hurtling through space in multiple directions simultaneously, carried along by a series of nested rotations and trajectories, each one faster than the last, and you feel none of it. The stillness you experience is not the stillness of something stationary, but the stillness of something moving so smoothly, with so little change in its motion, that your senses have no way to detect the velocity. You are, in a very real sense, a passenger aboard a vessel so stable that you have forgotten you are traveling at all. Let us begin with the rotation of the Earth beneath you, which is the slowest and most local of these motions, though it is still remarkably swift by any human standard. If you happen to be lying near the equator, at one of those latitudes where the planet's bulge is widest, then the ground beneath you is rotating eastward at approximately 1,040 miles per hour. This is faster than the cruising speed of most commercial aircraft, faster than the muzzle velocity of certain bullets. And yet you feel nothing. The air moves with you. The buildings move with you. The entire atmosphere and everything attached to the surface participates in this rotation, and so there is no wind from this motion, no resistance, no sensation of speed. You are like a passenger in a train car with the windows shuttered, unable to tell whether you are moving or standing still. This observation, that motion cannot be detected from within a smoothly moving system, was articulated with particular clarity by Galileo Galilei in the year 1632, in his great work comparing the competing models of the solar system. Galileo invited his readers to imagine themselves below the deck of a ship sailing smoothly across calm waters, locked in a cabin with no portholes, accompanied perhaps by butterflies and dripping bottles and small fish swimming in a bowl. He noted that the butterflies would fly equally well in all directions. The water would drip straight down. The fish would swim toward all sides of their bowl without preference. And no experiment performed inside that sealed cabin could reveal whether the ship was in motion or at anchor. This insight, which we now call Galilean relativity, explains why you do not feel the Earth rotating beneath you. You are inside the ship, and the ship's motion carries everything with it, including you, including the air you breathe, including every reference point you might use to judge your velocity. But the Earth is not merely rotating. It is also traveling around the Sun, following an elliptical path that takes 1 year to complete. And this motion is considerably faster than the rotation. At this moment, as you lie still, the Earth is orbiting the Sun at approximately 67,000 miles per hour. This is fast enough to cross the entire continental United States in about 3 minutes, fast enough to travel from the Earth to the Moon in under 4 hours. And still you feel nothing. The orbital velocity is so steady, the path so smooth, the acceleration so gentle compared to your body's sensitivity thresholds, that this tremendous speed produces no detectable sensation whatsoever. The mathematical description of this orbital motion was provided by Johannes Kepler in 1619, in a work whose full title translates roughly as The Harmony of the World. Kepler demonstrated that the planets move around the Sun in ellipses, sweeping out equal areas in equal times, following precise mathematical relationships between their orbital periods and their distances from the Sun. These laws allowed astronomers to calculate the orbital velocity of the Earth with great accuracy, and those calculations have since been confirmed by direct measurement using radar ranging and spacecraft tracking. The Earth moves through space at 67,000 miles per hour, and you move with it, perfectly unaware. The solar system itself, this collection of planets and moons and asteroids and comets, all bound by gravity to our local star, is also in motion. It orbits the center of the Milky Way galaxy, that vast pinwheel of several 100 billion stars, traveling along a path that takes approximately 230 million years to complete. The speed of this galactic orbit is approximately 514,000 miles per hour, which is nearly 8 times faster than the Earth's motion around the Sun. At this velocity, you could travel from New York to London in about 20 seconds. And yet, once again, you feel nothing. This motion, the rotation of the solar system around the galactic center, was discovered by the Dutch astronomer Jan Oort in 1927. Oort studied the apparent motions of stars across the sky and noticed a systematic pattern, a coordinated drift that could only be explained if the entire disk of the Milky Way was rotating, with stars closer to the center moving faster and stars farther out moving slower. His analysis revealed that our own solar system, located roughly 26,000 light-years from the galactic center, participates in this rotation, circling the galaxy at over 500,000 miles per hour. This discovery transformed our understanding of the Milky Way from a static cloud of stars into a dynamic, spinning structure, and it added another layer of motion to the already impressive list of velocities we never feel. But there is more. The Milky Way itself is not stationary. Our entire galaxy, along with dozens of smaller companion galaxies in what astronomers call the local group, is moving through the larger universe, drawn by gravity toward an enormous concentration of mass located roughly 150 million light-years away. This mass concentration, which contains thousands of galaxies clustered together in a region denser than the surrounding cosmic web, is called the Great Attractor, a name that conveys its gravitational influence even if the phenomenon itself remains difficult to observe directly because it lies behind the dusty plane of our own galaxy. The motion toward the Great Attractor was discovered in 1986 by a team of astronomers led by Donald Lyndon Bell, working with colleagues Sandra Faber, Roger Davies, and others. By carefully measuring the velocities and distances of many galaxies, they detected a systematic flow, a large-scale drift affecting not just the Milky Way, but hundreds of galaxies in our cosmic neighborhood. This drift carries us toward the Great Attractor at approximately 1.3 million miles per hour, or roughly 2% of the speed of light. At this velocity, you could circumnavigate the Earth in just over 1 minute, and still, lying in your bed, you feel absolutely nothing. The absence of sensation from these motions is not a failure of your senses, but a feature of how physics works. Your body can detect acceleration, the change in motion, but it cannot detect constant velocity, motion that continues unchanged. When you sit in an airplane flying smoothly at cruising altitude, you feel stationary. And you are not wrong to feel this way, because in the reference frame of the airplane, you are stationary. The coffee in your cup does not slosh toward the back of the plane. The flight attendants do not struggle to walk forward against some invisible wind, because within the airplane's reference frame, there is no motion to detect. The same principle applies to your bedroom. You are inside the Earth's reference frame, and so you move with it, and so you feel nothing. There is, however, a way to detect the Earth's rotation without looking outside, without reference to the stars, without any measurement involving things beyond our atmosphere. In 1851, the French physicist Jean-Bernard Léon Foucault demonstrated this method using nothing more than a very long pendulum suspended from the dome of the Panthéon in Paris. Foucault's pendulum swung back and forth in a fixed plane, as pendulums do, but over the course of hours, the plane of its swing appeared to rotate, slowly tracing out a circular path on the floor below. The pendulum itself had not changed direction. It was the floor beneath it that had rotated, carrying the observers around while the pendulum maintained its original orientation relative to the distant stars. This simple and beautiful experiment proved that the Earth rotates using only local measurements, and it remains one of the most elegant demonstrations in all of physics. So here you are, lying still, participating in all of these motions simultaneously. The Earth rotates beneath you at over 1,000 miles per hour. The Earth orbits the Sun at 67,000 miles per hour. The solar system orbits the galactic center at 514,000 miles per hour. The galaxy moves towards the great attractor at 1.3 million miles per hour. And these are only the motions we can measure directly, only the velocities we have managed to detect with our instruments and our mathematics. You are a passenger on a nested hierarchy of trajectories, each one carrying you through space at tremendous speed, and you feel none of it. But even this impressive accounting, this catalogue of cosmic velocities, does not capture the deepest motion of all. There is something else happening, something more fundamental than any of these spatial travels. And it was first described clearly in a lecture given on the 21st of September, 1908, by the German mathematician Hermann Minkowski at a scientific conference in Cologne. Minkowski had been one of Einstein's teachers at the Polytechnic in Zurich, and he had become fascinated by Einstein's special theory of relativity, published just 3 years earlier. In Cologne, Minkowski presented a radical new way of understanding what Einstein's equations were really saying about the nature of space and time. Henceforth, Minkowski told his audience, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. With these words, Minkowski introduced the concept that we now call space-time, a 4-dimensional structure in which the 3 dimensions of space and the 1 dimension of time are woven together into a single unified fabric. In this picture, nothing exists purely in space and nothing exists purely in time. Everything exists in space-time, and everything moves through space-time, always, continuously, without exception. And here is the remarkable thing, the quiet revelation that most people never encounter, the hidden motion that underlies all the others. You are moving through space-time right now, at a fixed and unchangeable speed, a speed that happens to equal the speed of light. This motion continues, whether you are lying still or running as fast as you can, whether you are aboard a spacecraft or resting at the bottom of a mine shaft. The speed cannot be increased and it cannot be decreased. It is not a choice. It is a fundamental feature of existence itself, as basic and unavoidable as having a position in space or a moment in time. This motion through time, this constant velocity through the temporal dimension, is what you are actually doing right now, as you lie still, as you breathe slowly, as you feel so convincingly stationary. You are traveling through time at the speed of light, and you have been doing so for every moment of your existence, and you cannot stop. In the year 1905, in a quiet Swiss city nestled along the banks of the river Aar, a young man of 26 years spent his days reviewing patent applications for electromagnetic devices, for improvements to watches, for various mechanical curiosities that inventors hoped might prove useful to someone somewhere. The city was Bern, and the street where he worked each day was called Kramgasse, a narrow cobblestone lane lined with arcaded buildings and small shops, where the famous Zitlog clock tower marked the hours with its mechanical figures and astronomical dial. The patent office itself occupied the 3rd floor of a sandstone building at number 49, and it was there, between assessments of other people's inventions, that a young patent clerk named Albert Einstein would quietly reshape humanity's understanding of space, time, and the very fabric of reality itself. His name was not yet famous, not in 1905, not by any considerable measure at all. He had struggled to find academic employment after completing his studies at the Swiss Federal Polytechnic in Zurich, and so he had taken this position as a technical expert, third class, at the Patent Office, a post that paid modestly but allowed him time to think. His supervisor, a man named Friedrich Haller, had encouraged him to work efficiently, to complete his patent evaluations quickly, and Einstein did so, leaving himself pockets of quietude throughout the day when he could turn his attention to the questions that had been turning over in his mind for nearly a decade. Questions about light, about motion, about the relationship between observers moving at different speeds. The office was neither grand nor particularly inspiring in its physical appearance, just rows of desks and the soft shuffling of papers. The occasional murmur of colleagues discussing this patent or that. But within this unremarkable setting, Einstein's thoughts ranged far beyond the electromagnetic devices described in the applications before him. He would later describe this period as his happiest time for scientific work, for the Patent Office asked relatively little of him intellectually, leaving his mind free to wander along the paths that most fascinated him. The question that had captured his imagination first arose when he was just 16 years old, still a student at a school in Aarau, Switzerland, where he had been sent after leaving Germany. At that young age, Einstein had tried to imagine something that might seem like a simple daydream, but which contained within it the seeds of profound difficulty. He asked himself what it would be like to chase a beam of light, to travel alongside it at the same tremendous speed, matching it perfectly so that you could observe the light wave as if it were standing still beside you. This thought experiment troubled him, though perhaps troubled is too strong a word, for he seems to have found a certain pleasure in sitting with the discomfort of contradictions. If you could ride alongside a beam of light, he reasoned, you would see the electromagnetic wave frozen in place, its electric and magnetic fields oscillating neither forward nor backward, simply hanging motionless in space like a photograph of a wave rather than a wave itself. But nothing in the equations of electromagnetism suggested that such a frozen wave could exist. The mathematics of James Clerk Maxwell, which described how electric and magnetic fields propagate through space, contained no solutions for stationary light. A frozen beam of light was not something the universe seemed to allow. For nearly 10 years, this peculiar thought experiment sat with him, sometimes at the front of his mind, sometimes receding into the background as he attended to his studies, his friendships, his eventual marriage, his work at the Patent Office. But it never left him entirely, this image of chasing light and finding something that ought not to be possible. Meanwhile, in the broader world of physics, another puzzle had been sitting unresolved since 1887, when two American scientists named Albert Michelson and Edward Morley had conducted an extraordinarily precise experiment in Cleveland, Ohio. Their goal had been to detect the motion of the Earth through a substance that physicists of that era called the luminiferous ether, a hypothetical medium that was thought to fill all of space and through which light waves were believed to propagate, much as sound waves propagate through air or water waves through the sea. The logic of their experiment was straightforward in conception, though demanding in execution. If the Earth were moving through this ether, then light traveling in the direction of Earth's motion should behave slightly differently from light traveling perpendicular to that motion, just as a swimmer moving with a current covers ground at a different rate than a swimmer moving across it. Michelson and Morley constructed an interferometer of remarkable sensitivity, a device that split a beam of light into two perpendicular paths, bounced each beam off mirrors, and then recombined them. Any difference in the speed of light along the two paths would show up as a shift in the interference pattern where the beams reunited. They expected to find a clear signal. The Earth orbits the Sun at approximately 30 kilometers per second, which is quite fast by everyday standards. And this motion through the ether should have produced a detectable effect. But when they performed their measurements, rotating their apparatus this way and that to test different orientations relative to the Earth's motion, they found nothing at all. No shift. No difference. The speed of light appeared to be exactly the same in every direction, regardless of how the Earth was moving through space. This null result was deeply puzzling to the physicists of the time. Various explanations were proposed, some involving the ether being dragged along by the Earth, others involving objects contracting in the direction of their motion through the ether. But none of these explanations felt entirely satisfying, and the Michelson-Morley result remained an awkward fact that the physics community had not yet fully digested when the young patent Clerk in Bern began writing his paper in the spring of 1905. What Einstein did, in a move of characteristic boldness and simplicity, was to take the constancy of the speed of light not as a puzzle to be explained away, but as a fundamental principle to be embraced. Rather than asking why light seemed to travel at the same speed, regardless of the observer's motion, he simply declared that this was how nature worked, that the speed of light in a vacuum was the same for all observers, period, regardless of how fast they were moving or in what direction. He combined this postulate with another, equally simple one, namely that the laws of physics should take the same form for all observers moving at constant velocity relative to one another. From these two assumptions alone, working through the mathematics with a clarity that required no reference to experimental data beyond what was already known, no citations of other researchers' work, Einstein derived a new theory of space and time. The paper he completed was titled On the Electrodynamics of Moving Bodies, and it was received by the journal Annalen der Physik on the 30th of June, 1905. It contained no bibliography, no footnotes referencing the work of others, just Einstein's reasoning laid out in careful, deliberate steps, as if he were explaining something that had always been true and was only now being noticed. The speed of light in a vacuum, which we now denote with the lowercase letter c, is 299,792,458 meters per second. This is not merely a very large number, though it certainly is that, nor is it simply the speed at which light happens to travel. It is something more fundamental, a kind of cosmic speed limit woven into the very structure of space-time itself. Nothing carrying information, nothing with mass, nothing capable of cause and effect can exceed this speed. It appears in equations far beyond those governing light, showing up in contexts that seem to have nothing to do with electromagnetic radiation, and it serves as a conversion factor between space and time, suggesting that these two aspects of reality are more deeply connected than our everyday experience would lead us to believe. What Einstein realized, and what his paper demonstrated through careful reasoning, is that if the speed of light is truly constant for all observers, then other quantities we had assumed to be constant must not be constant at all. In particular, time itself must behave differently for observers moving at different speeds. Consider two observers, one stationary and one moving past at high velocity. If both measure the speed of a beam of light, and if both obtain the same answer, then something must give. Speed is distance divided by time, and if the speed is fixed while the distance traveled appears different to the two observers, then the time elapsed must also appear different. The moving observer's clock, as measured by the stationary observer, must tick more slowly. This effect, which came to be known as time dilation, was not a quirk of perception or a limitation of measurement apparatus. Einstein was claiming that time itself, the actual progression of moments from past to future, ran at different rates depending on your state of motion. A clock moving relative to you would genuinely tick slower, not because anything was wrong with the clock, but because that is how time behaves in a universe where the speed of light is absolute. For decades, this prediction remained a theoretical curiosity, too subtle to measure with the clocks available in Einstein's era. But by the early 1970s, atomic clocks had become precise enough to detect the effect directly. In October of 1971, a physicist named Joseph Hafele and an astronomer named Richard Keating conducted an experiment that would have seemed almost absurd in its simplicity had the stakes not been so high. They placed 4 cesium atomic clocks aboard commercial airliners, the ordinary passenger jets that flew regular routes around the world, and sent them on a journey eastward around the globe, then on a separate journey westward. The clocks that traveled accumulated a different amount of time than identical clocks that remained stationary at the United States Naval Observatory. The differences were measured in nanoseconds, in billionths of a second, but they were real and they matched Einstein's predictions with remarkable accuracy. The eastward flying clocks, moving faster relative to the Earth's surface because they added their airspeed to the planet's rotation, ticked slightly slower. The westward flying clocks, moving against the rotation, ticked slightly faster. When the experimenters also accounted for another effect predicted by Einstein's later work on gravity, namely that clocks tick faster at higher altitudes where gravity is slightly weaker, the agreement between theory and measurement was striking. Atomic clocks flying on commercial jets had confirmed what a patent clerk had deduced from pure thought 66 years earlier. Time was not the universal constant that Newton had assumed it to be. Time was flexible, malleable, responsive to motion in ways that defied everyday intuition but yielded to careful mathematical description. And yet, this was only the beginning of the story. For if time itself changes depending on how fast you are moving, a natural question arises, one that Einstein's work would eventually answer in ways both beautiful and strange. The speed of light stands as an absolute limit, a boundary that nothing with mass can reach. Light travels at precisely this speed, always, in every reference frame, for every observer. But you, sitting or lying wherever you are at this moment, certainly do not feel as though you are moving at the speed of light. You feel stationary, or perhaps gently at rest. And yet, in a certain deep and mathematically precise sense, You are moving through the fabric of space-time at exactly that cosmic speed limit. At c itself, at 299,792,458 meters per second. The only question is how that motion is distributed between movement through space and movement through time. This is the thought we shall carry with us gently into the next part of our discussion. The idea that speed through space-time is not something you can change, only redirect, and that the very experience of time passing, of moments flowing from future into past, is itself a kind of motion, one you have been undertaking without pause since the moment you were born. In the early years of the 20th century, a mathematician named Hermann Minkowski stood before an audience in Cologne and offered a quiet revolution in how we might picture the universe around us. He had been Einstein's teacher once, and now he was about to take his former student's work and reshape it into something geometrically elegant. Something that would change how physicists speak about reality itself. Minkowski proposed that space and time, which we so naturally think of as separate things, as the stage and the clock, are in fact woven together into a single continuous fabric, a four-dimensional structure that he called space-time. He put it rather poetically, suggesting that space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This was not a minor adjustment to our understanding, not a small correction or a mathematical convenience, but rather a fundamental reimagining of what it means to exist in a universe like ours. To understand what Minkowski was describing, it helps to think first about ordinary space, the three dimensions we move through so easily every day. When you walk across a room, you can choose to walk straight ahead, or you can walk at an angle, or you can walk in any direction you please. And the room itself does not mind. The space simply accommodates your path. We measure distances in this space using a formula that feels almost intuitive. The Pythagorean theorem extended into 3 dimensions, where the distance between 2 points depends on how far apart they are in each direction. Forward and backward, left and right, up and down. The squares of these separations add together, and the square root of that sum gives you the total distance. This works beautifully for navigating a city or mapping the stars, and it served humanity well for centuries before anyone thought to question its deeper structure. But Minkowski noticed something peculiar in Einstein's equations, something that suggested time should be included in this picture, not as a separate backdrop against which distances are measured, but as a 4th dimension woven directly into the fabric itself. The formula that emerged was almost the same as the Pythagorean distance, but with one crucial difference. When you calculate what is called the space-time interval between 2 events, you add together the squares of the spatial separations just as before, but then you subtract the square of the time separation, after multiplying time by the speed of light to give it the same units as distance. This subtraction is the key, the signature of the geometry that Minkowski discovered, and it gives space-time its distinctive character. The resulting number, the space-time interval, turns out to be the same for all observers, regardless of how fast they are moving relative to each other. Different observers might disagree about the spatial distance between 2 events, and they might disagree about the time elapsed between them. but they will always agree on this combined interval. It is one of the universe's invariants, a fixed quantity that does not change depending on your perspective. This interval equation is not something you need to memorize or calculate, not for our purposes here, but it is worth letting the idea settle gently into your thoughts. The minus sign in front of the time component is what gives space-time its hyperbolic character, its non-Euclidean geometry, and it is why the rules of space-time feel so different from the rules of ordinary space. In regular geometry, the shortest path between 2 points is a straight line, but in the hyperbolic geometry of space-time, the longest proper time between 2 events is experienced along a straight path, what physicists call a geodesic. This inversion is subtle, and it underlies many of the strange behaviors that emerge when things move very fast or when gravity becomes strong. The physicist Brian Greene, who has spent much of his career explaining these ideas with patience and clarity, offers a lovely way to picture what is happening when we move through space-time. He describes it as being somewhat like a frozen river, a block of ice in which every moment of time is present all at once, embedded in the ice from source to sea. If you could stand outside this river and look at it from above, you would see not just the river as it is now, but the river as it was and as it will be, all frozen together in a single crystalline structure. Your own life, in this picture, is a path carved through the ice, a trajectory that extends from your beginning to your end, threading through the 4 dimensions of the block. This is what Hermann Weyl, writing in 1918, just a few years after Minkowski's original insight, called a world line, the complete history of an object's journey through space-time, traced out like a thread suspended in glass. Greene's analogy becomes even more illuminating when you consider motion. Imagine, he suggests, that you have a fixed amount of motion available to you, a total speed that never changes and that you cannot increase or decrease. If you are standing perfectly still in space, not moving forward or backward or in any direction, then all of this motion flows through the time dimension. You are, in effect, racing through time at the maximum possible rate. But if you begin to move through space, walking or driving or flying, some of that fixed total motion gets redirected, tilted away from the time direction and into the spatial directions. You are now moving through space, yes, but at the cost of moving slightly more slowly through time. The total remains the same, always, but the allocation between space and time has shifted. This is not a metaphor, though it sounds like one. It is a precise mathematical description of how motion works in the framework of special relativity. The invariant speed, the total magnitude of motion through space-time, is exactly equal to the speed of light, the quantity we call c, roughly 300 million meters per second. Every object in the universe, whether it is a photon of light or a planet or a person sitting quietly in a chair, moves through space-time at precisely this speed. There are no exceptions, no objects that move faster and no objects that move slower. The only difference between a beam of light and a resting stone is the direction of their motion through the 4-dimensional fabric. Brian Cox, the physicist and broadcaster whose gentle explanations have reached millions of listeners, has described this idea many times with characteristic care. He emphasizes that the speed of light is not merely a speed limit, not just the fastest anything can go, but rather the fundamental rate at which existence itself unfolds. Everything moves at c, always, through the union of space and time. A photon of light travels through space at c, and because all of its motion is directed through the spatial dimensions, it has none left over for time. From the photon's own perspective, if such a perspective could be meaningful, no time passes at all. It departs from a distant star and arrives at your eye in what is, for the photon, a single timeless instant. But you, sitting still and reading these words, are moving entirely through time, racing into the future at the speed of light while remaining stationary in space. Richard Feynman, in his famous lectures at Caltech in 1963, developed these ideas with his characteristic blend of precision and accessibility. He guided his students through the mathematics of special relativity with patience, showing how the transformation equations that relate different observers' measurements arise naturally from the geometry of space-time. Feynman was careful to emphasize that these are not mere curiosities or edge cases, not things that only matter for particles in accelerators or spacecraft near black holes, but fundamental truths about the structure of reality that apply equally to everything, everywhere, at all times. The effects are small at everyday speeds, far too small to notice, but they are never absent. Even now, as you breathe slowly and feel yourself drifting toward sleep, you are participating in this cosmic geometry, moving through the four-dimensional fabric in your own particular direction. The mathematics that underlies all of this is the mathematics of hyperbolic geometry, a non-Euclidean system in which the familiar rules of angles and distances are subtly modified. In ordinary Euclidean geometry, the angles of a triangle add up to exactly 180 degrees, and parallel lines never meet, and the circumference of a circle is precisely pi times its diameter. In hyperbolic geometry, these relationships change. The angles of a triangle sum to less than 180 degrees, and parallel lines can diverge, and circles have more circumference than you would expect for their size. Spacetime is hyperbolic in its structure, and this hyperbolicity is what prevents anything from exceeding the speed of light. What makes time dilation and length contraction inevitable consequences of motion? What ensures that the space-time interval remains invariant for all observers? To make this more concrete, physicists speak of something called the four-velocity, a mathematical object that describes not just how fast you are moving through space, but how fast you are moving through all four dimensions of space-time at once. This four-velocity is a vector, an arrow with both magnitude and direction, pointing along your world line through the fabric of existence. And the remarkable thing, the quiet but profound truth at the heart of special relativity, is that the magnitude of this four-velocity is always exactly c. It does not matter how fast you are walking or how still you are sitting. The length of your four-velocity vector is the speed of light, always and without exception. When you are at rest, your four-velocity points entirely in the time direction. All of your motion through space-time is motion through time, and the rate at which you move through time, your proper time, accumulates at the maximum possible rate. This proper time, often denoted by the Greek letter tau, is the time measured by a clock traveling with you. The time that ticks away on your wristwatch. The time you experience directly as your life unfolds. It is related to but distinct from coordinate time, the time measured by a stationary observer watching you from afar. For an object at rest, proper time and coordinate time are the same. But for a moving object, proper time passes more slowly, and the relationship between them is governed by the geometry of space-time. Hermann Weyl, who did so much to clarify and extend these ideas in the years following Minkowski's original insight, described world lines with great care in his 1918 writings on space-time geometry. He emphasized that every object, every particle, every person traces out a continuous path through the four-dimensional manifold, and that this path, the world line, is the complete history of that object's existence. The world line extends backward into the past and forward into the future, a thread of being woven through the fabric of space-time. Where you are now, reading these words, is a single point on your world line, and the direction your world line points at this moment, the direction of your velocity, determines how your future will unfold. If you could somehow see your own world line from outside, if you could step back and view the four-dimensional structure of space-time as Minkowski and Weyl envisioned it, you would see a long, gently curving thread extending from your birth to your eventual end, embedded in a vast and intricate tapestry of other world lines, other threads, some crossing yours and some running parallel, some ending abruptly and some continuing far beyond your own. Every interaction you have ever had, every person you have ever met, every object you have ever touched, corresponds to a point where your world line intersects or approaches another. The geometry is complex and beautiful, and it is all determined by the hyperbolic structure of space-time, by the minus sign in the interval equation, by the invariance of C. And so we arrive at a truth that is both simple and profound, a truth that the mathematics reveals with quiet clarity. When you sit perfectly still, when you cease all motion through space and let yourself rest completely, you do not become stationary. You cannot become stationary, because nothing in the universe is ever truly at rest. Instead, all of your motion is redirected into the time dimension, and you race through time at the speed of light, 300 million meters per second, hurtling into the future at the maximum possible rate. This is not a figure of speech, not a poetic exaggeration, not a way of making physics sound more dramatic than it is. It is measured reality, confirmed by countless experiments, embedded in the very structure of the equations that govern our universe. You are, at this moment, traveling through time at the speed of light, and you have been doing so for your entire life, and you will continue to do so for as long as you exist, because this is what it means to be a thing in space-time, a world line threading through the four-dimensional fabric, a traveler whose journey never slows and never stops. And so we arrive at the place where theory meets the physical world, where equations written in quiet studies must answer to clocks and towers and particles streaming through the upper atmosphere. Because physics, for all its abstraction, must eventually submit itself to measurement, to the patient work of experimentalists who carry their instruments up mountains, who fly them around the world, who send them into orbit and wait to see what the universe will confess, and what the universe has confessed, again and again, across decades of careful measurement, is that time truly does bend, that the relationship between motion through space and motion through time is not merely a mathematical convenience, but a feature of reality as fundamental as mass or charge or the speed of light itself. Let us begin in the autumn of 1971, when a physicist named Joseph Hafele and an astronomer named Richard Keating undertook an experiment that sounds almost whimsical in its simplicity, though its implications were anything but simple. They purchased airline tickets, commercial airline tickets on Pan American and Trans World Airlines, the ordinary carriers of business people and tourists and families traveling to see relatives. But Hafele and Keating were not ordinary passengers, because they brought with them cesium beam atomic clocks, 4 of them in total, devices capable of measuring time with an accuracy that would have seemed miraculous to any previous generation of scientists. Cesium clocks work by counting the oscillations of cesium atoms as they transition between energy states. And these oscillations occur with such regularity, such unwavering consistency, that the cesium atom's resonance frequency now defines the second itself. Hafele and Keating flew eastward first, circumnavigating the globe with their clocks carefully monitored, recording each moment as the aircraft traveled in the same direction as the Earth's rotation, adding its velocity to the considerable speed at which passengers were already moving, simply by standing on the planet's spinning surface. Then they flew westward, traveling against the Earth's rotation, effectively moving more slowly through space relative to the center of the Earth. Throughout both journeys, identical cesium clocks remained behind on the ground at the United States Naval Observatory, ticking away in their climate-controlled chambers, providing a reference against which the traveling clocks could be compared. When the experiment concluded and the numbers were examined with all the care that such measurements demand, the results matched the predictions of relativity with an exactness that left little room for doubt. The eastward flying clocks, which had moved faster through space, had accumulated fewer nanoseconds than the reference clocks, had aged slightly less during their journey around the world. The westward flying clocks, moving more slowly through space, had accumulated more nanoseconds, had aged slightly more. The differences were small, measured in billionths of seconds, in quantities so minute that they would be utterly imperceptible to any human sense or any instrument less refined than an atomic clock. But they were real, and they were precisely what Einstein's equations had predicted more than half a century earlier. There is something deeply reassuring about this kind of confirmation, about an experiment that anyone with sufficient funding and patience could replicate, that involves no exotic materials or extreme conditions, but merely aluminum aircraft and commercially available clocks and the patient willingness to fly around the world twice. The universe bent time for Hafele and Keating in exactly the way that theory said it would. Not approximately, not within some generous margin of error, but with the kind of precision that transforms speculation into settled science. And the bending of time has continued to reveal itself in technologies that now touch nearly every aspect of modern life. Consider the constellation of satellites that comprise the Global Positioning System, the first of which was launched in 1978, with the full network becoming operational in subsequent decades. These satellites orbit approximately 20,000 kilometers above the Earth's surface, moving at speeds of roughly 14,000 kilometers per hour, and they carry atomic clocks that must maintain synchronization with clocks on the ground if the system is to function at all. Because the entire purpose of the global positioning system is to measure time differences, to calculate how long signals take to travel from multiple satellites to a receiver on Earth, and to use those time differences to triangulate position with remarkable accuracy. But here is where relativity intrudes upon the practical business of navigation. The satellites are moving rapidly through space, and special relativity tells us that their clocks should tick more slowly than clocks on the ground, accumulating approximately 7 microseconds less each day. At the same time, the satellites are farther from the Earth's gravitational well, and general relativity tells us that this should make their clocks tick faster than ground-based clocks, accumulating approximately 45 microseconds more each day. The two effects work in opposite directions but do not cancel, leaving a net difference of approximately 38 microseconds per day, with the satellite clocks running faster overall. 38 microseconds may sound inconsequential, a quantity so small that one might reasonably wonder why anyone should care about it at all. But light travels nearly 11 kilometers in 38 microseconds, and positioning errors accumulate continuously, growing worse with each passing minute that the discrepancy goes uncorrected. Without relativistic corrections built into the system, positions calculated from GPS signals would drift by roughly 10 kilometers per day, which is to say, the system would be useless for any purpose more demanding than determining which continent you happen to be standing on. Every time you use a navigation application, every time a ship captain checks their position, or an aircraft follows an approach path, or a surveyor establishes a boundary, the calculations depend upon corrections that Einstein's theory made necessary and possible. We might travel further back, to 1960, to the Jefferson Physical Laboratory at Harvard University, where Robert Pound and Glenn Rebka performed an experiment that seems almost impossibly delicate in its conception. They wished to measure the effect of gravity on the flow of time, not the gravity of stars or planets, but merely the gravity of the Earth itself, acting across a vertical distance of just 22.5 meters, the height of the tower in which they worked. General relativity predicts that time passes slightly faster at higher elevations, where gravity is marginally weaker, and Pound and Rebka set out to detect this difference using gamma rays and the phenomenon known as the Mossbauer effect. Gamma rays were emitted at the bottom of the tower and absorbed at the top. But the absorption could only occur if the frequency of the arriving gamma rays precisely matched the resonant frequency of the absorbing atoms. And here is where the experiment becomes beautiful in its indirection. Because if time truly runs faster at the top of the tower, then the gamma rays arriving there would appear to have a slightly lower frequency than they possessed when emitted, shifted toward the red end of the spectrum by their climb against gravity. Pound and Rebka detected exactly this shift, a change of roughly 2 parts in 1,000 trillion, a quantity so small that its measurement required extraordinary care and ingenuity. But the measurement was made, and the result agreed with general relativity to within 10%, a confirmation later refined by subsequent experiments to even greater precision. Perhaps the most elegant confirmations of time dilation come from the natural world itself, from particles created not in laboratories but in the upper atmosphere, where cosmic rays collide with nitrogen and oxygen nuclei and produce showers of secondary particles that rain down upon the Earth. Among these particles are muons, somewhat heavier cousins of the electron, and muons have a curious property that makes them ideal witnesses to the bending of time. They decay, transforming into electrons and neutrinos with a half-life of approximately 2 microseconds when measured at rest. In 1941, Bruno Rossi and David Hall made observations on Mount Washington in New Hampshire that revealed something initially puzzling. Muons created in the upper atmosphere, some 10 kilometers above the mountain's summit, were arriving at the surface in far greater numbers than their short lifetimes should permit. Traveling at speeds approaching that of light, muons should have decayed many times over during their descent through the atmosphere, leaving only a tiny fraction to reach detectors on the ground. But far more muons were arriving than this calculation suggested, and the resolution of this puzzle lay in the dilation of time itself. From the muon's perspective, its lifetime remains the ordinary 2 microseconds. But from our perspective on the ground, the muon's internal clock runs slow, stretched by its tremendous velocity through space. A muon traveling at 99% of the speed of light experiences time dilation by a factor of roughly 7, which extends its apparent lifetime sufficiently for many more muons to survive the journey to the surface. The muons themselves do not know they are living longer, because from their own reference frame, they are not. But from our reference frame, watching them streak down through the atmosphere, they age more slowly than they would if they were standing still. And this slowing is exactly what allows them to reach our detectors in such abundance. This same phenomenon has been confirmed millions of times in particle accelerators around the world, at facilities like CERN in Switzerland, where particles are routinely accelerated to velocities so close to the speed of light that their time dilation factors reach into the thousands. Unstable particles that would decay in microseconds when at rest persist for milliseconds when traveling at such speeds. Their lifetimes stretched by the same mechanism that preserves the atmospheric muons, the same mechanism that slowed the clocks of Hafele and Keating as they flew eastward around the world. In 1976, NASA launched Gravity Probe AA, a spacecraft carrying a hydrogen maser clock, a timepiece of exquisite precision, to an altitude of 10,000 kilometers. The mission lasted less than 2 hours, but during that time, the onboard clock was compared continuously with reference clocks on the ground, and the results provided perhaps the most stringent test of gravitational time dilation yet achieved. The clock in space ran faster than its Earth-bound counterparts, exactly as general relativity predicted, with an agreement between theory and measurement that reached 70 parts per million, a confirmation so precise that it established the reliability of relativistic corrections for decades of subsequent applications. Each of these experiments, separated by years and continents and methodologies, whispers the same truth in its own particular dialect. The Hafele-Keating clocks speak of commercial aircraft and nanoseconds and the rotation of the Earth beneath them. The GPS satellites speak of microseconds and orbital mechanics and the practical necessities of navigation. The Pound-Rebka experiment speaks of gamma rays and towers and the subtle weight of gravity upon light itself. The muons speak of cosmic rays and mountain observatories and lifetimes stretched by velocity. And Gravity Probe A speaks of hydrogen masers and orbital trajectories and the careful work of comparing timepieces across the gulf between Earth and space. But all of them, in their different ways, are telling us the same story. The story of a universe in which motion through space and motion through time are not independent quantities, but aspects of a single underlying reality, trading against each other in ways that can be measured and predicted and relied upon. The speed of light stands at the center of this story. The invariant quantity that anchors all these relationships, the universal speed limit that determines exactly how much time must bend when space is traversed. And so we have arrived, through careful measurement and patient observation, at a truth that began as pure thought in the mind of a patent clerk in Bern and has since been confirmed so many times, in so many ways, that it has become part of the bedrock of modern physics. Time bends. Time slows for those who move. Time runs faster, far from massive bodies, and slower in the depths of gravity wells. These are not metaphors or approximations, but features of the universe, as real and as reliable as the ground beneath you. Features that reveal themselves whenever we look carefully enough, whenever we bring sufficient precision to bear upon the patient task of measuring what the cosmos is willing to tell us. And so we come to understand that this speed through space-time, this constant velocity of 300 million meters per second, is not merely a description of how things happen to be, but rather a fundamental constraint, a kind of budget that the universe enforces with perfect and unwavering precision. You might think of it as a cosmic allowance, a fixed quantity that every object, every particle, every speck of matter must spend, and the question is never whether to spend it, but only how to divide it between the two available directions, the direction through space and the direction through time. And this brings us naturally to wonder why it is that objects with mass can never quite manage to spend all of their allowance on motion through space. Why they can never redirect their entire velocity away from time and into the spatial dimensions. Why, no matter how much energy we pour into accelerating them, they approach the speed of light through space but never quite arrive. The answer lies in what happens to an object as it moves faster and faster. And to understand this, we must speak about a quantity that physicists call gamma, the Lorentz factor, named for the Dutch physicist Hendrik Lorentz, who worked out its mathematical form in the years just before Einstein published his theory of special relativity. Gamma is a number that starts at 1 when an object is at rest, and grows larger as the object moves faster. And the way it grows is rather gentle at first, barely noticeable at the speeds we encounter in everyday life, but becomes increasingly dramatic as the object approaches the speed of light. At half the speed of light, gamma has grown to about 1.155, a modest increase of 15%. At 90% of the speed of light, gamma has reached approximately 2.3. But at 99% of the speed of light, gamma has climbed to just over 7. And at 99.9%, it exceeds 22. And the pattern continues with ever steeper increases as we approach that final threshold. What gamma measures, in a sense, is how much the universe must adjust to accommodate an object's motion through space. It appears in the equations that describe time dilation, length contraction, and, most importantly for our present discussion, in the relationship between energy and velocity. You see, as an object moves faster, the energy required to accelerate it further does not remain constant, but increases in proportion to gamma, and this means that the closer an object gets to the speed of light, the more energy each additional increment of speed demands. This is sometimes described as an increase in the object's relativistic mass, though many physicists today prefer to speak simply of relativistic momentum and energy, finding the concept of changing mass to be somewhat misleading. But the essential point remains the same, that an object moving at high speed resists further acceleration more strongly than the same object at rest. And this resistance grows without bound as the speed of light is approached. To make this concrete, let us visit the great particle accelerators that physicists have built over the past century. Enormous machines designed specifically to push particles to the highest possible speeds and to study what happens when they collide. At the Stanford Linear Accelerator Center, known as SLAC, a beam of electrons travels down a corridor more than 3 kilometers long, gaining energy from microwave fields at each stage of the journey, until by the time they reach the end, they are moving at 99.99999% of the speed of light, a figure with 7 nines after the decimal point. The electrons at SLAC have a gamma factor of approximately 50,000, which means that the energy required to push them that final tiny fraction closer to the speed of light is 50,000 times greater than it would be to accelerate the same electrons from rest to a modest speed. And yet, even with all that energy, even with all that effort, the electrons have not reached the speed of light. They have only come extraordinarily close, and the gap that remains, though vanishingly small in absolute terms, would require still more energy to close, and more again, and so on without end. The pattern repeats at the Large Hadron Collider near Geneva, where protons rather than electrons are accelerated around a ring 27 kilometers in circumference, reaching speeds of 99.99999% of the speed of light, with a gamma factor of approximately 7,000. The protons at the LHC carry so much energy that when they collide, new particles are created from the energy itself, particles that did not exist a moment before, and the conditions at the point of collision briefly resemble those that existed in the universe a tiny fraction of a second after the Big Bang. And yet, even these protons, traveling so fast that they complete 11,000 laps around the ring every second, have not reached the speed of light, and they never will, no matter how much the machine is improved, no matter how much energy is supplied, because the gap between any finite speed and the speed of light can never be fully closed by any finite amount of energy. This is the asymptotic nature of the speed limit, the way it retreats as you approach it, always remaining just out of reach, like a horizon that recedes as you walk toward it. But unlike a horizon, which is merely a feature of perspective and can be reached if you walk far enough, the speed of light is a genuine boundary, a wall built into the structure of space-time itself. The energy required to reach it is not merely large, It is infinite. And since no physical process can supply infinite energy, no object with mass can ever travel through space at the speed of light. The cosmic ledger, as we might call it, simply does not allow it. And this brings us to a beautiful and clarifying contrast. Because there are particles in the universe that do travel at the speed of light through space, and they are able to do so precisely because they have no mass at rest. The photon is the most familiar of these massless particles, the quantum of light, the carrier of electromagnetic force. And for a photon, the mathematics of motion through space-time takes on a peculiarly simple and rather startling form. Because a photon has no rest mass, its gamma factor is undefined. Or rather, the usual formulas break down entirely, and the photon exists in a kind of limiting case where all of its space-time velocity is directed through space and none through time. A photon, in other words, does not experience time at all. Not in the sense that we experience it as a flowing sequence of moments, but in the sense that from the photon's own perspective, if we can even speak of such a thing, no time passes between the moment of its emission and the moment of its absorption. Consider a photon that leaves a distant star, a star perhaps 100 light-years away from Earth, and travels across the void to strike the retina of an astronomer gazing upward on a clear night. From the astronomer's perspective, the photon has been traveling for 100 years, crossing an immense gulf of space at 300 million meters per second, a journey of almost 1,000,000 billion kilometers. But from the photon's own perspective, if perspective is even a meaningful concept for something that does not experience time, the journey took no time at all. The emission and the absorption were simultaneous. The distance between the star and the eye was zero. This is not a metaphor or a simplification. It is what the mathematics of special relativity actually predicts, a consequence of the Lorentz transformation applied to a particle moving at exactly the speed of light. For a photon, the universe is contracted to a single point along the direction of travel, and the interval of time between departure and arrival is zero. And yet even photons, massless as they are, must obey the cosmic ledger in their own way. And the evidence for this obedience can be found in an experiment we have mentioned before, the Pound-Rebka experiment conducted at Harvard University in the autumn of 1959. In that experiment, gamma rays were emitted at the bottom of a tower and detected at the top, a vertical distance of just over 22 meters, and the photons were found to have lost a tiny amount of energy during their climb. Their frequency shifted ever so slightly toward the red end of the spectrum. The shift was minuscule, about 2 parts in a million, billion, but it was exactly what general relativity predicted, and it demonstrated that even light, even massless light traveling at the universal speed limit, must trade energy for gravitational potential as it climbs away from a massive body. The photon cannot slow down, because photons always travel at the speed of light through space, and so instead the photon loses energy in the only way available to it, by reducing its frequency, by shifting from blue toward red, by becoming, in a sense, a slightly less energetic version of itself. And when a photon falls inward toward a massive body, the reverse happens. It gains energy, its frequency increases, it blue shifts, and this too has been measured and confirmed countless times in experiments and observations around the world. The ledger balances, always and everywhere, and the photon's behavior is simply another expression of the same deep principle that governs everything else. The principle that motion through space-time is fixed at a constant total speed, and that changes in one aspect of that motion must be compensated by changes in another. And so we return to the question with which we began this section. The question of why we cannot slow down our journey through time. Why we are locked into this constant forward motion. Why we cannot choose to pause or to stop or to linger a little longer in the moments we love. The answer, as we now understand it, is that our speed through space-time is not negotiable. It is a fixed quantity set by the structure of the universe itself, and the only freedom we have is in how we divide it. When we sit still in a chair, reading perhaps, or drifting towards sleep, our entire space-time velocity is directed through time, and we move through time as fast as it is possible to move, at the rate of 1 second per second in our own frame of reference. When we move through space, we redirect a portion of our velocity away from time and into spatial motion, and our clocks slow down ever so slightly as a result, but the total speed remains the same. 300 million meters per second through the combined fabric of space and time. And this is not something we can change by any act of will or any application of force. The cosmic ledger, as we have called it, always balances. The photon spends all its velocity on space and none on time. The particle in the accelerator spends almost all its velocity on space, but a tiny fraction still flows through time, and that fraction cannot be reduced to zero no matter how much energy is supplied. And we ourselves, sitting or walking or flying or sleeping, spend almost all our velocity on time and only the smallest fraction on space, because the speeds we achieve are so very small compared to the speed of light. But in every case, for every particle and every person and every photon, the total is the same. The budget is fixed. The speed through space-time is locked at c, and this is not a rule imposed from outside, but a reflection of how space-time itself is woven together, how space and time are not separate things, but aspects of a single unified geometry. Let us consider now the photon, that most fundamental carrier of light, and what it might be said to know of time, if knowing were something available to it. This is a meditation of sorts, a quiet contemplation of what it means to exist without duration, to travel vast distances across the cosmos while experiencing, in some profound sense, nothing at all. The photon moves at the speed of light because it is light, and in moving at that speed, it surrenders entirely its claim to time. For the photon, there is no before and after, no waiting, no journey in the way that we understand journeys. There is only a kind of eternal present, if we can even call it present, stretched impossibly thin across what we, from our slower perspective, perceive as billions of years. Consider a photon leaving the surface of Proxima Centauri, our nearest stellar neighbor beyond the Sun, a red dwarf star sitting approximately 4.24 light-years from Earth. From our perspective here on this quiet planet, that photon undertakes a journey of considerable duration. We would measure its travel time as 4 years and roughly 3 months. give or take a few weeks, depending on the precise orbital positions involved. We might imagine it crossing the interstellar void, passing through the thin gas and dust of the local interstellar medium, perhaps encountering the occasional atom of hydrogen drifting in the darkness. We might picture it as a tiny traveler on a long road, patient and persistent, making its way toward us across an almost unimaginable distance. But this picture, comforting as it might be, does not capture what the photon itself experiences, if experience is even a word we can meaningfully apply. For the photon, the journey from Proxima Centauri to Earth takes no time at all. Not a very short time. Not a fraction of a second, so small as to be imperceptible, but precisely and exactly 0 time. The moment of emission from the star's surface and the moment of arrival at some detector on Earth, perhaps the back of someone's eye on a clear night, are from the photon's perspective the same moment. They are not separated by duration, because duration requires the passage of proper time, and proper time requires traveling at less than the speed of light. The photon, being massless and therefore compelled by the geometry of spacetime to move at exactly light speed, experiences a proper time interval of 0. It is born, and it arrives in what amounts to a single frozen instant. An instant that happens to be spread, from our vantage point, across more than 4 years of cosmic distance. This becomes even more remarkable, and perhaps even more peaceful to contemplate, when we consider photons that have traveled far greater distances. The cosmic microwave background radiation, that gentle glow of ancient light that permeates all of space, consists of photons that were released approximately 13.8 billion years ago, during the epoch of recombination, when the young universe cooled sufficiently for atoms to form and for light to travel freely without constant scattering. These photons have been traveling toward us for nearly the entire age of the universe. They carry information about conditions in the cosmos when it was only about 380,000 years old, a mere infant compared to its present venerable age. We detect them now with sensitive instruments, measuring their tiny temperature fluctuations, mapping the seeds of all the galaxies and clusters and vast structures we see today. And yet, for each of these ancient photons, no time has passed. The moment of release from that hot primordial plasma and the moment of absorption by a detector on a satellite orbiting Earth are, from the photon's perspective, simultaneous. 13.8 billion years of travel, crossing distances so vast that light itself, the fastest thing in the universe, required nearly the entire history of the cosmos to traverse them. And yet, the photon experienced none of it. The journey was instantaneous. Or rather, the concept of journey does not apply. The photon did not wait. It did not age. It did not experience the passage of eons while galaxies formed and stars were born and died and new stars formed from their ashes. All of that happened in our frame of reference, not in the photons. The physicist Paul Davies, known for his thoughtful explorations of time and cosmology, has reflected on what this might mean for our understanding of existence and temporality. Davies has noted that the photon's perspective, while not literally a perspective in any conscious sense, challenges our intuitions about what it means to exist in time. We tend to think of existence as something that happens over a duration, as a process that unfolds moment by moment. But the photon's existence, if we can call it that, is not a process at all. It is something more like a single point, a connection between two events in space-time that happens to involve no temporal separation for the thing making that connection. This is not a failure of the photon to experience time properly. It is simply what existence means for something without mass, something that must move at the maximum cosmic speed limit. The philosopher of physics, Tim Maudlin, whose careful analyses of space-time and causation have illuminated many subtle aspects of these questions, has explored the implications of special relativity for our understanding of temporal passage. Maudlin has argued that time is not an illusion, that the passage of time is a real and fundamental feature of the universe, not merely a psychological impression created by our conscious minds. And yet, the photon seems to exist outside of this passage. For Maudlin, this does not diminish the reality of time, but rather highlights the profound difference between massive and massless existence. We, with our mass, are embedded in time's flow. We cannot escape it, cannot speed it up or slow it down beyond the modest variations allowed by our motion and gravitational environment. The photon, by contrast, is not embedded in time at all. It exists in a kind of timeless connection between events, a thread linking two points in the fabric of space-time without any temporal thickness to that thread. There have been experiments, careful and precise, that have appeared to slow light down, and these are worth understanding because they reveal something important about what light truly is and what it means to move at the speed of light. In 1999, the physicist Lene Vestergaard Howe and her colleagues at Harvard University achieved something remarkable. Using a Bose-Einstein condensate, a state of matter in which atoms are cooled to temperatures so close to absolute zero that quantum effects dominate their behavior, Howe's team was able to slow a pulse of light to a speed of approximately 38 miles per hour. This is slower than a bicycle, slower than a person running, absurdly slow for something we think of as the fastest phenomenon in the universe. 2 years later, in 2001, the same team went further, bringing light to a complete standstill within the condensate, holding it in place before releasing it to continue on its way. These experiments are extraordinary achievements of precision and control. But it is important to understand what they do and do not tell us about the nature of light. The light that was slowed and stopped in these experiments was interacting with matter in a very specific and carefully engineered way. The Bose-Einstein condensate created conditions in which the light pulse was effectively absorbed and re-emitted by the atoms of the medium in a coherent fashion, passing its information from atom to atom in a kind of slow relay. The individual photons involved were not themselves traveling slowly through vacuum. Rather, the light pulse as a collective phenomenon was being handed off through a dense quantum medium, its effective speed reduced by the interactions that carried it along. In the vacuum of empty space, where no such interactions occur, light still travels at exactly the speed of light, unchanging and eternal in its velocity. A more subtle finding came in 2015, when a team led by Miles Paget at the University of Glasgow demonstrated that even in free space, structured light, whose wavefront has been shaped into particular patterns, can travel slightly slower than unstructured light. The slowing in these experiments was extremely small, measurable only with the most precise instruments, but it was real. The photons in the structured beam arrived at their destination fractionally later than photons in an unstructured beam traveling the same distance. This experiment expanded our understanding of how the shape and structure of a light beam can affect its propagation. But again, it did not contradict the fundamental principle that light in vacuum travels at a constant speed. The structuring of the beam introduced a kind of effective path length or phase delay that accounted for the slower arrival, not a change in the fundamental velocity of the photons themselves. What these experiments teach us is that light is a subtle phenomenon, capable of interacting with matter and with itself in ways that can modify its apparent speed, while preserving the underlying constancy of photon velocity in vacuum. They remind us that the speed of light is not merely a speed, but a structural feature of space-time, a boundary condition that shapes the geometry of causality itself. Nothing with mass can reach this speed, and nothing massless can move at any other speed in vacuum. The photon does not choose to move at light speed. It has no choice. Its masslessness determines its velocity absolutely, and that velocity in turn determines its relationship with time, which is to say, its complete absence of relationship with time. For massless particles, all of existence is a single frozen moment. There is no duration, no sequence, no experience of events unfolding one after another. The photon does not wait for anything because waiting requires time, and time requires traveling at less than light speed. The photon does not remember its emission because memory requires earlier and later, and for the photon there is no earlier and later. The photon does not anticipate its absorption because anticipation requires a future that has not yet arrived. And for the photon, arrival is indistinguishable from departure. This is not a deprivation. It is simply a different mode of existence, one that we, with our massive bodies and our unavoidable embedding in temporal flow, cannot directly access or fully comprehend. And this brings us back to ourselves, to our own situation as massive beings moving through space-time. We cannot become photons. We cannot shed our mass and join that timeless realm of instantaneous connection. Every particle in our bodies, every atom and molecule possesses mass and therefore possesses a relationship with time that cannot be escaped. We move through time at the speed of light, as we discussed earlier, but this motion is not something we can stop or even slow down in any meaningful way. We can shift some of that motion from time into space by moving faster through the universe, and in doing so, we can experience time more slowly relative to others who are not moving with us. But we can never reach the limit. We can never become timeless. This is not a tragedy. It is simply what it means to be the kind of thing that we are. The photon, for all its timelessness, does not experience anything. It does not know the slow unfolding of a summer afternoon, the gradual warming of coffee in a favorite mug, the patient growth of a child into an adult. These experiences require time, require duration, require the gentle accumulation of moments into memories. We are beings for whom time passes, and in that passage, we find everything that makes existence meaningful to us. The photon travels across the cosmos in an instant and knows nothing of the journey. We travel through our lives more slowly, moment by moment, and in that slowness, we find room for thought and feeling and understanding. The photon connects events without experiencing them. We experience events by dwelling within time, by moving through it at the only pace available to creatures of mass, which is the pace of time itself, steady and inescapable, and, in its own quiet way, deeply reassuring. And so we come now to the broader view, the wider river, if you will, the place where our journey along this strange current of time meets the great tributaries of thought that physicists and philosophers have been charting for more than a century, and where we might rest for a moment to consider what it all means, or whether meaning is even the right word to use when speaking of something so fundamental that it seems to precede meaning itself, something so woven into the fabric of existence that asking what it means may be a bit like asking what existence means, which is perhaps a question best left for another evening, another slow drift into sleep. But for now, let us simply float here and observe the landscape of ideas that surrounds us. There is a physicist named Julian Barber who lives in a small village in England, and who has spent much of his life thinking about time in a way that might seem strange at first, but which carries a certain quiet beauty once you let it settle into your thoughts, like sediment settling through still water. In his book from 1999, called The End of Time, Barber proposed something rather remarkable, which is that time, as we experience it, may not exist at all in the fundamental equations of the universe. What exists instead, he suggests, is a vast collection of moments, each one complete in itself, each one containing within it the arrangement of every particle and field and grain of sand and distant star. And these moments do not flow from one to the next like water in a river, but rather they simply are, all of them, in a kind of timeless library that Barber calls Platonia, a place where every possible configuration of the universe sits quietly on its shelf. And what we experience as the passage of time is merely our consciousness moving through this library, or perhaps not even moving, but simply being aware of one page at a time, each page containing the memory of all the pages that came before it, so that the feeling of flow, the sense of duration, emerges not from time itself, but from the structure of these frozen moments, from the way they relate to one another in the mathematics of the universe. This is a difficult idea to hold in one's mind, and you need not hold it tightly. You may let it drift past like a leaf on the surface of our river, but it is worth knowing that serious physicists have considered the possibility that time is not a fundamental feature of reality, but rather something that emerges from something deeper, something more still and more silent than the ticking of any clock. Carlo Rovelli, an Italian physicist who works on a theory called loop quantum gravity, has proposed something called the thermal time hypothesis, which suggests that what we call time may emerge from our particular way of interacting with the world, from our limited knowledge of all the microscopic details of the systems around us. In this view, time is connected to entropy, to the gradual spreading out of energy and order that we will speak of shortly. And what feels like the forward march of moments is actually a statistical phenomenon, arising from the way that large collections of particles tend to move from less probable arrangements to more probable ones. Ravelli's work sits at the frontier of physics, in that misty region where quantum mechanics and gravity have not yet been reconciled, and his ideas are still being tested and debated, but they carry within them the suggestion that time itself may not be as fundamental as space or matter, that it may be something that crystallizes out of more basic ingredients, like frost forming on a window, beautiful and intricate, but secondary to the cold air and the glass. And then there is the block universe, a concept that has been championed by physicists like Max Tegmark of MIT, and which follows rather directly from the geometry of spacetime that Einstein revealed to us. In the block universe picture, the past and the present and the future are all equally real, all existing together in a four-dimensional structure where your 10th birthday is just as present, just as actual, as this very moment in which you are listening to these words. The block universe does not move. It does not flow. It simply is. And what we call now is merely a label we attach to our current position within it, like a pin stuck into a map to mark where we happen to be standing. This view is sometimes called eternalism, and it suggests that when we say the past is gone and the future has not yet arrived, we are speaking from our own limited perspective, like an ant crawling along a garden path who cannot see the beginning or the end, but only the small patch of ground beneath its feet. Einstein himself seems to have held something like this view, and in March of 1955, just a few weeks before his own death, he wrote a letter to the family of his dear friend Michel Besso, who had recently passed away, and in that letter, Einstein offered a gentle consolation, saying that the distinction between past, present, and future is only a stubbornly persistent illusion. This was not meant as cold comfort, but as a kind of peace, a suggestion that Besso had not been extinguished, but had simply moved beyond the narrow slice of spacetime that Einstein still occupied, that somewhere in the vast block of existence, Besso was still laughing, still thinking, still sharing coffee and conversation. Because in the block universe, nothing is ever truly lost. It is only elsewhere, only else when. Not all physicists agree with this picture, of course, and it would be unfair to suggest that the question has been settled, because it has not, and may never be. And that is part of what makes physics a living enterprise, rather than a finished monument. Lee Smolin, an American physicist who also works on quantum gravity, has argued in his book Time Reborn from 2013 that time is not an illusion at all, that it is the most real thing there is, that the flow of moments and the openness of the future are genuine features of the universe and not mere appearances to be explained away. Smolin suggests that the laws of physics themselves may evolve over time, that the universe is not a static block but a creative unfolding, and that treating time as an illusion may cause us to miss something essential about the nature of reality. His view is a minority position among physicists, but it is held with conviction, and it reminds us that even at the highest levels of theoretical physics, there is room for disagreement, for alternative visions, for the humble acknowledgement that we do not yet know everything. What nearly everyone does agree upon, however, is the connection between time and entropy, between the direction of the river and the gradual spreading out of order and energy that seems to characterize our universe. This idea goes back to the work of Ludwig Boltzmann in the 1870s, an Austrian physicist who struggle to understand why heat flows from hot objects to cold ones and never the other way around. Why cream stirred into coffee never spontaneously separates back out. Why we remember the past but not the future. Boltzmann's answer was statistical, a matter of counting possibilities, of noticing that there are vastly more ways for things to be disordered than ordered, vastly more arrangements of atoms that look like a mess than arrangements that look like a structure. And so any system left to itself will tend to wander toward disorder simply because disorder is so much more probable. This tendency is what we call the increase of entropy, and it seems to define the arrow of time, the difference between forward and backward, the reason why we age and decay and cannot unscramble our eggs. And yet even here there are mysteries, puzzles that keep physicists awake at night, or perhaps lull them into a different kind of sleep, a dreaming contemplation of why the universe began in such a low entropy state in the first place, why there was so much order at the beginning to be gradually dispersed. This is sometimes called the past hypothesis, and it remains one of the deep unsolved problems of cosmology, a question that connects the direction of time to the origin of everything. In recent years, between 2019 and 2023, there has been a growing body of research on quantum clocks and the emergence of time, experiments and theoretical work that probe the very foundations of temporal experience. Some of this research suggests that time may be an emergent phenomenon, arising from quantum entanglement and the way that different parts of the universe become correlated with one another. Other work explores the possibility that at the smallest scales, at the Planck scale where quantum gravity becomes important, the smooth flow of time may break down entirely, may dissolve into something grainy and discontinuous, like the pixels of a digital image that look smooth from a distance but become blocky when you zoom in too close. These are still early days for such research, and the results are tentative. But they point toward a future in which our understanding of time may be as different from the present as our present understanding is from the clockwork universe of Newton. Stephen Hawking, who passed away in 2018, once proposed a curious idea called imaginary time, which sounds like something from a children's story, but is actually a mathematical technique for exploring the very early universe. In imaginary time, time, which is measured using imaginary numbers in the mathematical sense, the distinction between time and space becomes blurred, and the singularity at the beginning of the universe may be smoothed away, replaced by a gentle rounding like the curve of a sphere. Hawking suggested that asking what came before the Big Bang might be like asking what is north of the North Pole, a question that seems meaningful but actually points to the limits of our concepts rather than to any real place. Imaginary time is not the time we experience, not the river that carries us forward, but it may be a useful way of thinking about the boundaries of existence, about the edges of the map where our ordinary ideas break down. And so we return to the question that underlies all of this, the question that has been with us since we began this gentle journey, which is why time feels like it flows if we are simply moving through it. If the block universe is real and all moments exist equally, if time is perhaps not fundamental at all, but emergent from something deeper and stranger. This is sometimes called the problem of the flow of time, or the problem of temporal passage, and it has occupied philosophers as much as physicists, because it touches on consciousness itself, on what it means to be a creature that experiences moments one after another rather than all at once. The answer, if there is one, may lie in the structure of memory, in the way that each moment contains within it the traces of the moments that came before, so that the feeling of flow is built into the fabric of experience rather than added on from outside. Or the answer may lie in thermodynamics, in the increase of entropy that gives time its direction and makes each moment different from the last. Or the answer may lie in places we have not yet imagined, in theories not yet written, in the quiet contemplation of some future physicist who is perhaps right now a child falling asleep, dreaming of rivers and light. What we can say, as we drift here at the end of this section, is that you cannot slow down because there is nowhere else to redirect your cosmic velocity. No side road to turn onto, no brakes to apply. Space and time are the only directions available to you, the only dimensions through which you can travel. And see, the speed of light is your eternal and unchangeable speed through the combination of them. If you try to move faster through space, you will simply move slower through time, and the total will remain the same. Always see, always that constant hum beneath the surface of existence. You are a passenger on a river that carries everything, every atom and every star, every memory and every hope, and the river flows at exactly one speed, the speed of light through space-time. And there is no way to step off, no way to swim against the current, no way to linger at one bend in the river while the rest of the universe flows past. You are carried, gently and inexorably, through the landscape of moments. And whether those moments exist all at once in a timeless block or unfold genuinely into an open future, you will experience them one by one, like pages turning in a book you cannot put down, like the slow and steady breathing that is perhaps even now drawing you closer to sleep. And so we arrive, gently, at a kind of cosmic perspective, one that places you, lying quietly wherever you are, within the vast and ancient context of everything that has ever been. You are still now, or nearly still, your body at rest, your breathing slow, and yet you are moving through time at the fastest speed the universe permits, which is to say, you are traveling at 299,792,458 meters every second. 1 second of duration for every second that passes, an unbreakable rhythm, a cosmic heartbeat that has accompanied you since the moment you began to exist and will continue without interruption for as long as you continue to be. This is not a metaphor, though it sounds like one, and it is not an exaggeration designed to make you feel small or insignificant, but rather a simple description of how space-time works, how your velocity must always equal the speed of light, how that magnificent constant divides itself between your motion through space and your motion through time and your motion through time, and how, because you are lying still, nearly all of that tremendous speed is carrying you forward through duration, through the quiet accumulation of moments, through the gentle passage from 1 second to the next. Consider, if you will, the Hubble Space Telescope, that patient instrument orbiting approximately 540 kilometers above the Earth, circling our planet once every 97 minutes, looking outward into the darkness. In December of 1995, Astronomers pointed this telescope at a tiny patch of sky, a region so small it would be covered by a grain of sand held at arm's length, a seemingly empty region in the constellation Ursa Major, where previous observations had revealed very little of interest. And then they left the telescope's camera open for 10 consecutive days, allowing photons to accumulate on the detector, gathering ancient light one particle at a time. The resulting image, known as the Hubble Deep Field, revealed something that still invites quiet contemplation. In that tiny patch of apparent emptiness, there were approximately 3,000 galaxies, each one containing billions of stars. Some of these galaxies so distant that their light had been traveling for nearly 13 billion years before reaching the telescope's mirror. Which is to say that the photons collected during those 10 December days had begun their journey when the universe was young, when the first generations of stars were still forming, when the cosmos looked nothing like it does today. And yet, those photons had been moving toward us all that time, traveling at the speed of light through expanding space, until finally, after all those billions of years, they arrived at a telescope orbiting a small blue planet and were recorded on a detector and translated into an image that humans could see. And here is something worth considering as you rest. Many of those ancient galaxies, perhaps most of them, no longer exist in the form they had when that light was emitted. 13 billion years is a long time, long enough for stars to be born and to die, long enough for galaxies to merge and transform, long enough for the brilliant blue stars visible in the deep field to have exhausted their nuclear fuel and collapsed billions of years ago. What we see in that image is not what exists now, but what existed then, a kind of temporal archaeology made possible by the finite speed of light. And when we look at those distant galaxies, we are looking not across space alone, but across time, seeing the universe as it was in its youth while simultaneously existing in its present. The James Webb Space Telescope, which began its scientific observations in 2022, has extended this temporal archaeology even further. With its infrared instruments and its position at the second Lagrange point, approximately 1.5 million kilometers from Earth, this telescope has observed some of the earliest galaxies ever detected, light that has been traveling through the universe for more than 13 billion years, light that was emitted only a few 100 million years after the Big Bang itself, when the cosmos was still assembling its first structures. In 2022, 2023, and 2024, the James Webb Space Telescope revealed galaxies that formed earlier and grew larger more quickly than many models had predicted. Galaxies whose stars were already producing heavy elements in those early epochs. Galaxies that challenge and refine our understanding of cosmic evolution. And all of this knowledge comes to us as light, as electromagnetic radiation that has been moving through space-time while those ancient stellar populations were living and dying, while their galaxies were merging with neighbors and growing and transforming, while billions of years of cosmic history unfolded between the emission of those photons and their arrival at our instruments. Those ancient stars, in all probability, no longer exist. They have completed their nuclear burning and ended their lives in whatever manner their masses required. Some as white dwarfs cooling slowly toward darkness. Some as neutron stars spinning in silence. Some as black holes from which no light escapes. But the photons they emitted are still traveling, still carrying information about conditions in the early universe, still moving at the speed of light through the dimension of time, just as you are doing at this very moment, just as everything is doing, always, without exception. In February of 1990, the Voyager 1 spacecraft, which had been traveling outward from Earth since its launch in September of 1977, took a photograph at the request of the astronomer Carl Sagan. The spacecraft was approximately 6 billion kilometers from Earth at that time, beyond the orbit of Neptune, looking back toward the inner solar system, and in that photograph, the Earth appeared as a tiny point of light, less than a single pixel in size, suspended in a scattered ray of sunlight. Sagan called this image the pale blue dot, and in 1994 he wrote about what it meant to him, about how that tiny point contained everyone you have ever heard of, every human being who ever lived, all our joys and sufferings, all our wars and our love affairs, all our history and all our future, gathered together on a mote of dust suspended in a sunbeam. This reflection was not intended to diminish human significance, but to provide perspective, to remind us that we live on a small world in an immense cosmos, and that the vastness of space and time is something we participate in, whether we think about it or not. Sagan understood that when we look at the night sky, we are looking back in time, that the stars we see are not as they are now, but as they were when their light began its journey, that the universe reveals itself to us through the patient accumulation of ancient photons, and that our place in this cosmic story is both humble and remarkable. Voyager 1 continues its journey outward, even now, and has traveled more than 15 billion miles from Earth, well beyond the heliopause where the solar wind gives way to the interstellar medium. It still sends radio signals back to Earth, though its power supply diminishes year by year, and those signals, traveling at the speed of light, take approximately 22 hours to reach us. When mission controllers send a command to Voyager 1, they must wait nearly 2 days for a response, because the signal must travel outward through all that space, and the response must travel back through that same distance. And light, even though it is the fastest thing in the universe, still requires time to cross such immense separations. This is communication stretched across space-time, a conversation conducted at the fundamental speed limit of the cosmos, and it reminds us that the universe is large beyond easy comprehension, and that our connections to distant places require patience and time, that even light, moving at 300,000 kilometers per second, cannot be everywhere at once, cannot bridge vast distances instantaneously, cannot exceed the velocity that space-time itself permits. You are a time traveler. This is not a fanciful claim, but a literal description of your situation. You are moving through the dimension we call duration at the maximum possible rate, 1 second per second, the speed of light expressed as a journey through time rather than space. You have been doing this since you were born, and everything around you has been doing it too, and there is no way to slow down and no way to stop, because this motion through time is simply what it means to exist in a universe structured the way ours is structured, in a space-time that obeys the geometry Einstein described. And there is something gentle about this, something reassuring, because it means that time is not something that happens to you from outside, but something you move through, like a swimmer moving through calm water. And though you cannot choose your speed, you are nevertheless participating in the journey, traveling forward through duration alongside everything else that exists. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn antenna at Bell Telephone Laboratories in Holmdel, New Jersey, trying to detect radio signals bounced off balloon satellites. They encountered a persistent noise in their data, a faint hiss of microwave radiation that seemed to come from every direction equally, that did not vary with time of day or season. That could not be explained by any local source they investigated. They even removed pigeons from the antenna and cleaned away what they politely called a white dielectric material. But the hiss remained. What Penzias and Wilson had discovered, though they did not immediately realize it, was the cosmic microwave background radiation, the oldest light in the universe, electromagnetic radiation that was emitted approximately 380,000 years after the Big Bang, when the cosmos had cooled enough for hydrogen atoms to form and for light to travel freely through space. This ancient light has been traveling ever since, cooling as the universe expanded, stretching from visible wavelengths into the microwave part of the spectrum, filling all of space with a gentle whisper of thermal radiation at a temperature of approximately 2.7 degrees above absolute zero. When you tune an analog radio or television between stations and hear static, a small fraction of that noise, perhaps 1%, consists of photons from the cosmic microwave background, ancient light that has been traveling for nearly 14 billion years before arriving at your antenna. This is the universe's oldest light, the afterglow of creation itself, and it surrounds you even now, passing through the walls and through your resting body, filling the room with a gentle hiss of electromagnetic radiation that began its journey when the universe was less than 500,000 years old. This ancient light accompanies your eternal voyage through time. It has been traveling alongside everything else in the cosmos, moving at the speed of light through the dimension of duration, carrying information about the early universe, whispering quietly in the microwave frequencies, reminding us that we exist within a cosmos that has a history, that had a beginning, that has been unfolding for billions of years and will continue to unfold for billions more. You are part of this unfolding. Your motion through time is the same motion that carries light across the universe, the same motion that has been happening since time itself began. And as you rest here, breathing slowly, moving through duration at the speed of light, you are surrounded by the most ancient photons in existence, the cosmic microwave background whispering gently from every direction, the universe's oldest light keeping you company on your journey through time. There is nothing you need to do about any of this. It is simply happening, as it has always been happening, as it will continue to happen, the quiet progression of moments, the gentle accumulation of duration, the speed of light carrying you forward through time at 1 second per second, the cosmic heartbeat that has accompanied everything since the beginning and will continue until the end. And so you may rest now, knowing that you are moving, that you have always been moving, that your journey through time continues, whether you are awake or asleep, and that the ancient light of the universe whispers alongside you, a companion on the voyage, a gentle reminder that you exist within something vast and old and ongoing, and that your rest tonight is simply another moment in the long unfolding of duration. One more second passing at the speed of light. One more heartbeat of the cosmos carrying you gently forward.